Hi guys, welcome to Electronics to the Point. In this video, we will see the impulse signal, which is an unmanageable signal by nature, and how to manage the impulse signal so that we can apply it in different signals, analyzing of different signals. You see, we know the mathematical equation that del of t, that is impulse del of t, I am considering the continuous time signal, is defined as at 0 its value is undefined value. I am considering infinity, but we have to think that it is undefined value. Mathematical equation f of t is equal to 0 for t not equal to 0, time axis, and this is the value axis. And f of t, it is not equal to 0 where at t equal to 0, right? This is the definition of impulse signals represented by del of t. Now this is an unmanageable signal because its value tending to infinity. So what we do is we have to define a manageable parent signal for this impulse so that we can make use of that parent signal and we make the evaluations making use of it with other signals. And in the process we are going to discuss two topics, that is, and topics are nothing but they are properties of this impulse. First one, time scaling property, and second one is time shifting property. Now let me propose a manageable parent signal. First, the manageable parent signal see what it has to define is manageable parent signal should be in similar to the impulse signal itself, and we know that area of del of t is unity. This is the meaning of impulse signal. So now how to design this parent signal? See, let me consider a signal which is symmetric about the value axis, that is from minus a by 2 to a by 2. Let me consider a rectangular pulse so that this height of this manageable parent signal is 1 divided by this upper limit a by 2 minus of this lower limit is equal to 1 by a. This is the height or magnitude of this manageable parent signal. And see, what is the width? Upper minus lower, a by 2 minus of minus a by 2, width is a, width equal to a, and this is the height. Now what is the area of this? Area is nothing but this rectangular pulse length into this width, okay. See, area is equal to 1 by a into width a. What we get? Area equal to 1. Now we can say that if we tend a to 0, that is limit a tends to 0, what happens? This coordinates will become 0. A by a where we have substitute 0 by 2 is nothing but 0. Here also 0. If we put 0 here, we will get the value infinity, so that letting a tends to 0, we get the same del of t, right? How? So from this we can say this del of t value which is tending to infinity at the value 0, we can say that this can be a parent signal, right? By using this we can solve the other signals which are involved by dealing this signal. So that now we have to remember 3 key points regarding this manageable parent signal. See, first point, this signal has to be finite one. See, I have defined a finite one, right? Minus a by 2 to a by 2, it is a finite signal. First one is signal is finite, and second point is width has to be reciprocal to height. See, our width is a, width should be reciprocal to height. The same width a and height is 1 by a, so the value is same, right? A is inversely proportional to a. This is width, this is height. This is the second property. And the third property it has to satisfy is the area under this plot has to be 1. As we know, area under impulse is 1, right? So area has to be unity. Unity is nothing but 1, right? Now we have defined this manageable parent signal in terms of this is the step response, right? Now let us apply some properties of this impulse signal. That is first one, time scaling property. From the time scaling property, what we can say is whenever we consider a signal, that is we considering this parent signal. See, I am considering the same parent signal minus a by 2 to a by 2. Let this be f of t, or it can be defined as del of t with height a. And what I am defining, first one is time scaling. In the time scaling property of impulse, we can get del of at is nothing but scalar a is multiplied by t. That is, we can say that scaling operation has been done. How we have to represent this? See, f of at is, del of at is nothing but f of at, right? So what, okay, let us consider del of bt, as we have taken the coordinates as a, so let me take another one b, f of bt. What happens, what is meant by scaling operation? From a previous video we can observe some scaling. What it does is it divides the time axis variables by the scaling amount. So this minus a by 2 divided by b is nothing but scaled version is minus a by 2b minus a by 2b. And the point to be remembered is this is f of bt, right? The point to be remembered is the scaling operation does not affect the magnitude part, so magnitude remains same. Okay, this is del of bt, right? Now compare the properties. What we have said, signal has to be finite. From this graph we can say it is finite. Second one, width has to be inversely proportional. What is the width here? A by 2b minus of minus plus a by 2b is 2a by 2b. Width is a by b, right? Now let us consider this is width. What is height? That is amplitude is 1 by a. Width a by b inversely proportional to this is height, right? A inversely proportional to a, this satisfied, right? That's it. And third property, area has to be 1. So what we can say, this when we tend a to 0, this value tends to infinity, so area under del of t will be 1, right? See, now let us calculate the area. What we have said, area is this width into this height, 1 by a into a by b. What we get? 1 by b. Now we can say that scaling operation is leaving us with a value of 1 by b. Now if we consider del of bt, what happened, this got transformed to with a magnitude 1 by b with del of t. So what we can say, scalar part gets divided by the input impulse signal. So this is the time scaling property. Now let us consider, as we know impulse signal is an even signal. How we can say impulse is an even signal? See, this is the del of t. If we put del of minus t, what will be the value? There will be no translations by 180 degrees, as there is only one point existing at 0. So del of minus t is equal to del of t. So from even properties, del of t is a even signal, so we cannot get any negative values. So what we can say, 1 by modulus of b into del of t. This scaling property we can represent it as like this. If we are given with del of minus 2t, then transformation becomes 1 by modulus of minus 2 del of t. Minus 2, when it is modulus, it becomes positive, 1 by 2 del of t. This is the answer. This is how we apply scaling property. Now let us go to shifting property. After knowing some valuable points in shifting property, we will apply a problem. Second one is shifting property. Before going to shifting property, let us see the sampling property of impulse. Sampling property. What is meant by sampling? Sampling is nothing but the representation of, let us consider the f of t, let it be a continuous time signal like this, tending to infinity, tending to infinity. If we want to find at a specific point, let us consider at this point we want the value. So when we multiply it by a impulse signal somewhere around this point, let us consider this one 1. Here if we put the impulse at 1, we can find the sampled value at f of t, right? This is f of t into del of t. So from this continuous time signal we got, if we want a single point, by multiplying with the impulse function at that specific point, we can get back the sampled point of the continuous signal. So what we can say, by multiplying by multiplying impulse signal with the continuous time signal, we can get the samples. So what we can say, if this is f of t, if we are multiplying with del of t minus a, what happens? Let t minus a equal to 0, t equal to a, that is positive a. So at a, t is equal to a. This is the impulse. What is this? Del of t minus a. If we multiply with del of t minus a with f of t, we get at point a, this is a sampled value we got. What is this? F of a into del of t minus a. This is how we get this. If we are multiplied impulse function at origin, then what we get? Impulse at origin. If we are multiplying with this, we get f of t multiplied by del of t. Then what we get is at 0 we get defined a sampled value of f of 0 into del of t. This is the sampling property. How we can represent in generalized form? F of t multiplied by del of t plus or minus a. Why plus or minus a? It may be this side of origin or this side of origin. If del of t minus a, then we can get the positive side. If del of t plus a, when you equate it to 0, t equal to minus a, left side of the origin point also we can get. So what will be the transformation? F of a into del of t minus t plus or minus a. This is how we will get the sample values. If we multiply del value with the continuous same signal, we will get like this. Let us take example. If we are multiplying f of t with del of t plus 2, then what we get? F of minus 2 into del of t plus 2. This is the value we get. Okay, t equal to minus 2 value has to be placed in f of t. Okay, if we are given with del of t, okay, t minus 4 into f of t, then what we get? T equal to 4 has to be placed in f of t. F of 4 into del of t minus 4. These are some examples of sampling property. Now going to shifting property. Shifting property of impulse is nothing but it is the area property we have to consider. That is, whenever the impulse value we are defining, it is in the limits of the required input, so that the augment of impulse get shifted into input function. Okay, that is, in let minus infinity to infinity, integration from minus infinity f of t del of t. This how to represent shifting property. In the interval of minus infinity to infinity, del of t value exists at 0, so the del of t is included in this interval. So what happens is, del of t only defined at origin, right? So the shifting property, it defines only f of 0. Okay, here in sampling property we multiplied with the impulse, so that the value got, when we place that value, but the impulse multiplication is remained same. But in shifting property, we can say the impulse which is under the area where it is included, that value is shifted into input. That is, let us consider another. This is the representation of shifting property. If we consider minus infinity f of t into del of t minus a. Okay, what is t minus a? At positive point, this is the impulse defined at t equal to a, del of t minus a, right? Now from shifting property, what we can say, the augment will be shifted to here, I told. So at t equal to a, f of a. This is how we represent the shifting property. These are the two important properties. So what we can say, if we are considered integration minus 1 to 4 del of f of t into del of t plus 5, I considered t plus 5, but at what we can say, t plus 5 equal to 0, t equal to minus 5, but t equal to minus 5 is not included in this interval, right? So this impulse is not included in this limit. So what we can say, answer is 0. This is the important point we have to remember. Okay, impulse value has to be included in the limits, then only we can put this value in the input function. Okay, now let us take an example. Integration of minus infinity to infinity cos of pi of t minus 2 divided by t square plus 4 into g of t dt. G of t is nothing but an impulse function defined at g of t equal to with a magnitude 5 into del of t plus 3. Let us consider this. Then how we can define this g of t? G of t can be defined as at del of t equal to -3, impulse value is 5, area, this magnitude value is 5. So if we are multiplying with this signal, what happens? From the shifting property, at t equal to t plus 3 equal to 0, t equal to -3, what we are doing? See, integral minus infinity cos of pi into t minus 2 divided by t square plus 4 into 5 del of t plus 3 dt. See, as limits are from minus infinity to infinity, del of t equal to -3 value is included in this limit. So what we can do, the t equal to -3 has to put inside this t, so that what happens, integration minus infinity, this magnitude comes out 5 into cos of pi into t equal to -3 minus 2 divided by -3 whole square plus 4 dt is equal to 5 into cos of minus theta. This is cos of minus 5 pi. Minus theta is nothing but cos theta itself, right? So cos of 5 pi, what is the value of cos of 5 pi? Cos of 5 pi is 1. So 5 into 1 divided by, sorry, this integral goes away after the multiplication of impulse. So 3 square is 9 plus 4. What is the value? 5 by 13. This is how we apply the shifting property. These are some properties of impulses. In the next video we will see what is sampling function. Thank you.